Welcome back yet again to our final installment of the first installment of the series on trigonometric identities and such like. This time we are going to finally get to the heart of the matter, determining for a fact that an equation is actually an identity. Remembering that before we were able to show when something wasn't an identity just by finding that one exception that was enough to undo it being true everywhere. Just trying other stuff and having it work every time you tried it is not really enough to say one way or another. So now we're finally going to dive in and see when a function is in fact an identity. Good times. So in this video I will be showcasing all of the various approaches and strategies and other things that people like to use whenever they're trying to verify identities are actually identities. And we'll start with the simplest one first. The end goal here is to say, for instance, with what I have here, that the left-hand side, this equation here, is always true. So the left-hand side of my equation is always equal to the right-hand side. Or in other words, this left expression is actually the exact same as the right hand, just written in a different way. And so one way to go about doing that is to just take one side, be it the left or the right, and just apply algebra techniques or substitutions or cancellations or anything we can think of, really, to turn it into the other side. And so the first strategy I'll tell you about is just pick the side that looks more complicated, that has more going on, and that will give us more modes of ingress, more inlets, more avenues of progress to turn into the simpler looking side. So for here, this example, I've got cotangent over cosecant, and that's my left-hand side, and I'm claiming that's exactly identically equal to what I would have gotten with just cosine. So if I were to take just the left-hand side, cotangent divided by cosecant, well, that's the same as cotangent times 1 over cosecant, or in other words, cosine over sine times sine over 1. And lo and behold, those signs cancel, leaving me just with cosine x, which is the right-hand side. So using just the definition of cosine, the definition of cotangent, the definition of cosecant, sines of cosines, and the like, I have proved beyond shadow of a doubt that these are actually the same expressions. They are truly equivalent all the time. So this is, in fact, an identity. Now that said, this is for a fairly simple-looking one, I admit, I agree to that. But had you worked with maybe two expressions that were complicated, what you could do is start with one and keep going until you can go no further with that one. And if you can't go any further and you haven't reached the end, I would say don't just throw up your hands and erase everything you did and start fresh. Hold on to that and instead take the equation you didn't start with, take the expression that you didn't work with, and see if you can work that down to be, if not the left-hand side, then maybe any of the things you found along the way while you were reducing the left-hand side. Because if you can get the left-hand side and the right-hand side to individually come out to equal some third expression, then by the transitive property, they're all the same. So you could, if you really wanted, work with each side individually and hopefully meet in the middle. Ideally, though, you could just take one expression and reduce down to the other. That would be ideal. That said, though, working with each side individually is not the same as working with both sides at once. It's not the same as treating this truly as an equation and trying to solve for x or anything like that. So a bit of a cautionary tale here. A non-strategy would be, well, dividing by 0, obviously, but to explain what I mean, let's start and think about this. If you are going to prove something is an identity, you need the steps you take to be truly reversible. For instance, let's say I take the left-hand side and turn it into the right-hand side, then I would need to be able to do those same steps in reverse to take the right-hand side and turn it into the left-hand side. So some things that you can't do would be squaring both sides of an equation. For instance, let's say I had negative x equaling x. My algebra tells me that that's only true at x equals 0, not everywhere else, so it's not an identity. And yet, if you were to square both sides, you would get x squared equals x squared, which is an identity. But squaring both sides is not reversible. If you were to take the square root of this to get back to the original, you wouldn't get the original. You would get plus or minus x equals plus or minus x, and which plus or minus do I take? And since you can't really correctly answer that, there's no correct answer for that, that is not something you could do on the road to finding something being an identity. But to tie into the dividing by zero thing, another thing you can't do would be multiplying both sides of the equation by zero. So let's say I had some mess equaling some other mess, and I just multiplied both sides by zero. Well, that tells me then that 0 equals 0, which is an identity. So I'm good, right? Well, except not really, because what happens if I were to reverse your steps? I would have to do the opposite of multiplying by 0. I'd have to divide 0 to both sides of my equation, and well, that's not a thing that can be done. So just multiplying both sides by 0 isn't really a proper way of illustrating anything. So the short version here is just don't try to change the value of your expressions. Just take one expression and work with it, doing algebra techniques and simplifying, and hopefully getting to the other one. Or failing that, taking each in turn and working with each individually until you find something that is common to both. You can do that too. Now there's a lot of ways to simplify expressions. It's not just writing things in sines and cosines, combining fractions, and that sort of thing. As I mentioned in the last video, we can also work smart instead of hard. I could use existing identities, right? I could take something proved to be equivalent ways of writing existing expressions and substitute accordingly. Right now, we only really have access to the Pythagorean identities, being sine squared plus cosine squared equals 1. And of course, their variants, dividing everything through by sine squared gets me 1 plus cotangent squared equals cosecant squared, and also dividing through by cosine squared gets me tangent squared plus 1 equals secant squared. So those are things that we can always substitute, which might be handy for trying to prove that this equation is actually an identity. The equation being that 1 minus cosine squared times 1 plus cosine squared is equal to 2 sine squared minus sine to the fourth. And well, you may say, okay, I'm going to start with the more complicated side, which I presume to be 1 minus cosine squared times 1 plus cosine squared, and maybe you would want to multiply that out, giving you 1 minus cosine to the fourth of t, and I can't deal with that. I have a Pythagorean identity for 1 minus cosine squared, but not for 1 minus cosine to the fourth. So that's not really panning out. And for this side, the 2 sine squared minus sine to the fourth of t, I guess I could factor out a sine squared, but I don't think that's going to get me anywhere closer to where I want to go either. So here's what I say we do. I say we use the Pythagorean identity, sine squared plus cosine squared equals 1. And what I do is I take that and I substitute it into each of these two factors. So I'm going to rewrite this 1 as sine squared plus cosine squared. And then I'm also going to change up a little bit in here as well. Right, so the 1 becomes sine squared plus cosine squared. But also, right, this expression, this equation can be used to say, well, cosine squared is equal to 1 minus sine squared. And I'm going to substitute that into the second factor. And then cleaning this up a little bit, I've got sine squared, right, because this cosine squared and negative cosine squared will cancel. And that's being multiplied onto 2 minus sine squared. And distributing does give me the right-hand side. Perfect. So this is a totally valid strategy that could be used to clean up expressions to prove new identities. You can use known knowledge to find new knowledge. That's a very mathematical thing. Also, a very mathematical thing would be doing nothing. And I say that rather cutely, but you can, if you never change the value of an expression, do whatever you want to it. There's two ways to go about that. One is by adding 0. So for instance, let's say I had sine squared x plus 1 equaling 2 minus cosine squared x. There's a few ways to do this, but you could say sine squared x plus 1 is actually equal to sine squared x plus 0 plus 1, with the 0 is going to be equal cosine squared x minus cosine squared x. That's still 0, right? I've not changed the value of this left-hand side. But in having done that, I've got now sine squared plus cosine squared, which is 1. I've got this 1, and I'm left with negative cosine squared x, which is the right-hand side. That's pretty exciting. Also, the other one we could do is just multiply by 1. I don't really want to get into that in interest of time, but you can check example 5 in the textbook. It's actually pretty good. It does a pretty good job of explaining what that's all about. And one last thing here, one last example before we'll close out. If all else fails, if you can't turn the left-hand side into the right-hand side, if you can't turn the left and the right individually into some third expression, if the identities you can think of or have access to don't just seem to be panning out, if all else fails, you can just rewrite everything as sines and cosines and go from there. So suppose I wanted to prove cotangent plus tangent is actually equal to the product of secant times cosecant. And that might offend some sensibilities, but hear me out. If you wanted to prove this, maybe you could take the left-hand side. Maybe you could write that as just products of sines and cosines. Cotangent's cosine over sine. Tangent is sine over cosine. And suppose then that you recognize, oh, now that I've done this, I'm looking at a sum of two fractions. Let's get those combined. Get a least common denominator, add them up. I've got cosine squared plus sine squared over sine cosine, which is just 1 over sine times cosine. Split that up, 1 over cosine, 1 over sine, and that is secant cosecant. That is your right-hand side. So if you can't see what to do, perhaps, and oftentimes it will be the case, that writing things in cosines and sines will illustrate what needs to be done. So that's just one last thing to hold on to. And lastly, I just want to tell you what's going to come down the road now. Now that we're able to show when expressions can be simplified into maybe producing identities of our own, or when we have equalities and equations, which I can then show to be identities or not, what we're going to do now is start building on our knowledge. We're going to add more and more identities into the mix, and we're going to use those identities to maybe evaluate more complicated trig expressions, and also prove still more identities. It's going to be a very exciting time. It's going to be a very trying time for some. But I think with this approach, we will have a good enough result. So look forward to it, and I'll see you soon.